Okay, now I think we're in business. So I'm going to go back to sharing my screen. And go back to question number, the B part. Okay, so in fact, let me go back to my writing pad. Okay, so I'm sorry about that, folks. So let me just continue with this. So as I said before, I need to find the number of moles of the acid, right? So of course we do that. We do like what we did the last time. We take the volume, 6.00 mils. We convert that to liters. So we're gonna have 1 liter over 1,000 mils. And then multiply that by the molarity of the acid, which is 0.200 moles per liter. And according to my calculations, this works out to be equal to 1.20 times 10 to the minus 3 moles. All right. So we have the moles of the sodium hydroxide. We have the moles of the acid. What we need to do next is to write down the balanced equation for the reaction between the sodium hydroxide and the acid. And of course, that gives you sodium acetate and water. And of course, we set up our ice table. Initially, we're going to have 6.00 times 10 to the minus 4 moles of sodium hydroxide. And then for the acid, it's going to be 1.20 times 10 to the minus 3 moles. And then we have none of that and none of that. Well, this we don't need to concern ourselves with. And then at equilibrium, we can clearly see that the sodium hydroxide is going to be the limiting reactant. So all of it would be used up. And an equivalent amount of, an equal amount of the acid will be used up as well. And then as far as the sodium acetate is concerned, the amount of that produced would be the same. And then at, so this is a change actually. At the end of the reaction, you're going to have 0 here. This will give you 6.00 times 10 to the, oh, this should be minus 4 here. This should be minus 4 here. So this is going to be 6.00 times 10 to the minus 4 moles. And this is going to be 6.00 times 10 to the minus 4 moles. And if I recall, this is similar to the result that we got the last time. Ultimately, the concentration of the acid is going to be the same as the concentration of the sodium acetate, which would be the 6.00 times 10 to the minus 4 moles over the volume. And the volume would be the sum of 6 mils plus, what was the volume before? 6 mils, well, it doesn't really matter, whatever the volume is, right? Because since this is equal to this, as we saw the last time, the pH of that solution will be equal to the pKa of the acid, which will be minus log of Ka, which is, according to the question, 1.75 times 10 to the minus, what was it? 1.75 times 10 to the minus 5. So when we work that out, according to my calculation, the answer becomes 4.76. In fact, to be more specific, let me see here, 1.75 times 10 to the minus 5. And then I find the log of that, minus sign, it would be 4.75 7. All right, because we have 3 decimal places here due to the fact that we have 3 sig figs here. All right, so this here would be the final answer to the question. All right, so that one is similar to what we did in the A part, because in both of these cases, the concentrations of the acetate and the acetic acid are both the same. Remember, this is based on the Henderson-Hasselbalch equation. And let me just remind you what the Henderson-Hasselbalch equation is. Let me squeeze it in right here. It is pH is equal to pKa plus log of the concentration of A minus divided by the concentration of HA. Right? And because this is equal to this, that's 1, log of 1 is 0, so therefore the pH is equal to pKa. All right? Okay, so that's basically how that is done. Any questions about this one? Any questions? Any questions? Any questions? Okay, is it okay for me to get rid of this? Going once? Going twice? All right, so let me do this. And now we're going to move on to the C part. Now, I think the C part is going to be a bit different. Let me see here what the C part says. Okay, so this time in the case of the C part, we're going to titrate the same amount of sodium hydroxide with 6.00 mils of a 0.100 m butanoic acid solution. And it gives you the Ka for the butanoic acid as being equal to 1.52 times 10 to the minus 5. All right. So we're going to start off similarly. Again, the number of moles of sodium hydroxide calculated previously is what we're going to use here. That is equal to 6.00 times 10 to the minus 4. And in the case of the acid, the butanoic acid, I'm going to use HB to represent it. So the number of moles of HB would be equal to the volume, so this is moles, the volume, which is 6.00 mils, multiplied by 1 liter over 1,000 mils, converted from milliliters to liters, and then we multiply that by the concentration, which, according to the question, is 0.100 moles per liter. And when I did that calculation, I got 6.00 times 10 to the minus 4 moles. All right. So in this case, we have the sodium hydroxide reacting with the acid, and the products would be the sodium salt, sodium butanoate, plus H2O. All right. So initially, we're going to have 6.00 times 10 to the minus 4 moles of the sodium hydroxide. We're going to have 6.00 times 10 to the minus 4 moles of the acid. We're going to have none of this and none of this, all right? So my question to you is, what do you think the respective changes going to be? In fact, we need to ignore the water here. So what do you think will be in the next line for the changes? Anybody? What would be the change for the sodium hydroxide?
I don't know how to decide that because I don't see a limiting reactant. They're both the same amount.
Exactly. You're exactly right about that observation. They're the same amount. What that means, therefore, is that both of them are limiting.
So would both of them get used up completely then?
Exactly. So you're going to have minus 6.00 times 10 to the minus 4 moles here. Whoops, moles here. Same thing here. And then what do you think is going to happen as far as the sodium butanoate is concerned? What would be the change?
Square,
I'm sorry?
would you square the 6.00 times 10 to the minus 4?
No, 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 no. If 1 mole of this reacts with 1 mole of this, then how many moles of this would be produced?
Just one.
Exactly. So if this amount reacts with this amount of the acid, then how much of this you'd expect to be produced?
You're gonna have 6.00 times 10 to the
Exactly.
negative 4.
So plus 6.00 times 10 to the minus 4 would be the amount, would be the change. So therefore, at the end of this reaction, you're going to have none of that there remaining, none of that here, and the only thing that would be left would be the sodium butanoate, 6.00 times 10 to the minus 4 moles, all right? So the next thing we need to do now is to determine the molarity of the only thing remaining, which is the NaB, which by the way would be the same thing as the concentration of B minus, right? So that would be equal to 6.00 times 10 to the minus 4 moles. And then we divide by the volume. Now the total volume, let me create a little box over here. The total volume would be the volume of the sodium hydroxide, which is, let me see here. I have to scroll back up. I know it's 6.0 plus something, 6.0. If I remember correctly, it's 12, but let me confirm that by scrolling up here. Oops, scroll too fast. Yes. So plus 12.00 mils. So that gives 18.00 mils. So the 18.00 mils will go down here. But of course, we have to convert that to liters. 1 liter over 1,000 mils. That's a conversion factor. And we work that out. So when we work that out, let me get my calculator here. It's going to be equal to 0.0067. No, wait a minute. I'm doing something wrong here. There's 0.0333. Okay. 0.0333 M. All right. So that would be the concentration of the conjugate base, B minus. Okay. Now, here's the thing. The question is asking for the pH. So now what we have to do is look at what happens when B minus reacts with water, right? Because B minus, remember, is a conjugate base. It's going to react with water to form the hydroxide ion. And therefore, if we can find the concentration of the hydroxide ion, then we can determine ultimately what the pH is. Okay, now in order for me to do that, I need to erase all of this that I have here because I'm going to need some more space. So is it okay for me to get rid of this?
Yes.
All right, so let me do that now. So now what I'm going to do,
Yes.
I'm sorry? Oh, I thought somebody said something. Okay, so what we're going to do now is take the base, the conjugate base, and write the equation for the hydrolysis of that base. All right? Whoops, OH minus, all right? So initially, we had 0.0333 M of the conjugate base resulting from the previous reaction. We have none of that, none of that. So the change here is going to be minus X. Remember, we have to say minus X. We don't know what the change is because remember, the system is in equilibrium. And the change for the HB would be plus X. And the change for the hydroxide will be plus X. So at equilibrium, you're going to have 0.0333 minus X. Here you're going to have X, and here you're going to have X. So we can write down the KB expression for this, which is X over, or I should say X squared. Well, let me do it stepwise. Let me erase this here. So the KB expression is going to be concentration of HB. Okay, I chose the wrong pen. Ooh, wait a minute. Which one did I chose the wrong one. All right, let me go back to this here. Concentration of HB times the concentration of OH minus, all divided by the concentration of B minus. All right. And then I put in the terms, you're going to end up with x squared here over 0.0333 minus x. Again, we assume that x is much smaller than 0.0333. So that means that implies that 0.0333 minus x is approximately equal to 0.0333. So therefore, that means that KB is equal to x squared over 0.0333. So therefore, x will be equal to the square root of KB times 0.0333. Now, we are not given the KB value for the conjugate base, but we're given Ka for the acid. So we know the relationship between Ka and Kb is that Ka times Kb is equal to Kw. So therefore, Kb will be equal to Kw divided by Ka. So therefore, we can put that here. Under the square root sign, we're going to have this is Kb. So we're going to have Kb is equal to Kw divided by Ka times 0.0333. And then we put the numbers in. Kw is 1.00 times 10 to the minus 14. Ka is, what was it? It was given earlier in the question. Let me see if I can find it here. 1.52 times 10 to the minus 5. And we multiply that by, let me see if I can, I'm just going to put an arrow here to show what should be there, 0.0333, all right? And then we work this out. So according to my calculations, when that's worked out, that gives X works out to be equal to 4.68 times 10 to the minus 6. All right? So that is X, which is also equal to the concentration of OH minus, which is equal to this, right? So therefore, we can find the pOH. I'm going to put that up here. pOH is equal to minus log of 4.68 times 10 to the minus 6. And when I work that out, that works out to be equal to 5.33. So therefore, the pH would be equal to 14.00 minus 5.33. And according to my calculation, that works out to be equal to 8.67. So this would be the final answer right there. All right. Okay. Any questions about this? Any questions? Any questions? Okay. I need to step away for a minute. I'll be right back. Okay, I'm back. So if there are no questions on this, then may I erase this? Going once? Going twice? Okay, so let me get rid of this. Whoops, did the wrong thing there. Okay. I'm trying to remember which one of these was the one that I used. Not that one. Definitely not that one. Okay, let me use this one here. All right. So let me go back to the worksheet, the assignment. And the next question talks about, so this is a KSP problem, all right? Now, in this case, they're asking for the concentration of a saturated silver acetate solution, all right? Now, they did not specify whether or not it's the, hold on, let me see here. If they're asking for the molar concentration or the solubility in grams per liter. I'll just show you how to do all of them, all right? In fact, I don't think I need to move to the writing pad for this one. All right, so let me do this. Okay, what's going on here? Okay, let me do. Okay, let me do this, and let me go back. Oh shoot! Okay, hold on. Okay, now we're in business. All right, so let me start off by writing down the equation for the dissociation. That would be Ag C2H3O2 dissociating to form Ag plus C2H3O2 minus, all right? So KSP for this. Oh, before I even do that, let me show the ice table for this one here. So initially, we don't need to concern ourselves with the silver acetate because it's a solid. However, initially, the concentration for the silver ion would be 0 initially, and the concentration of the acetate ion would be 0. Now, the change here, if S is equal to the solubility of this compound, then the change here for the silver ion would be plus S, and for the acetate ion is going to be plus S. So therefore, at equilibrium, you're going to have S and S here, which means that KSP is equal to the concentration of Ag plus times the concentration of C2H3O2 minus. That's the equation for KSP. And all we have to do is plug in these two terms where these concentration expressions are. So you're going to have S times S equals S squared, which means that S is equal to the square root of KSP, which is equal to the square root of 1.94 times 10 to the minus 3. And that's basically what we do. So 1.94 times 10 to the minus 3. And then we find the square root of that. And according to my calculations, this works out to be equal to 0.440. Let me write that here. 0.440 M, right? So that would be the molar solubility. If the question is asking for the solubility in grams per liter, then what you'd have to do is take the 0.440 moles per liter and convert it to grams per liter. In other words, you're going to need to find out what the molar mass of the silver acetate is. Let me see if I can find that out quickly. So for the acetate, for the, oh, wait a minute. Where did I get that from? Okay, so for silver acetate, So according to what I have here, the molar mass of the silver acetate is 166.91 grams. So when you multiply 166.91 times 0.440, the answer I got is 73.4 grams per liter. All right, so that's the solubility in grams per liter, and this is the solubility in moles per liter. All right. Okay, any questions about this particular question? Any questions? Okay, so can I clear this? Going once, going twice. Okay, let me clear this. All right, so scrolling down now, in the case of the next question, it's actually asking you to do the opposite of what you did before. Of course, the numbers will be different because we're dealing with a different compound. In this case, they're asking for, or actually no, it's let me see here. Oh, no, it's asking for the same thing. It's asking for the concentration, but things will be a bit different because you're dealing with a different compound. Okay, so let me see here. First thing I would do is like what I did before. I am going to write down the equation for the dissociation. So in this case here, it's PbCl2 dissociating to form Pb2 plus 2Cl minus. And of course, let me just do this here. The Ksp for this will be equal to the concentration of Pb2 plus times the concentration of Cl minus squared. All right. So again, I'm going to set up the ice table. Initially, you're going to have 0 and 0 of these two. Now, if the solubility is S, we put here S equals solubility. If the solubility is S, then the change in the concentration of lead 2 plus is going to be plus S, and that, in the case of the chloride minus, would be plus 2S. So therefore, at equilibrium, you're going to have S, and you're going to have 2S here, and I'm going to plug these terms into this equation right here, and I'm going to end up with Ksp is equal to S times 2S squared, right? Because S represents the concentration of Pb2 plus, 2S represents the concentration of Cl minus. So we can simplify this to get this being equal to 8S cubed. Because 2 squared, no, actually 4S cubed, my bad. What am I doing? 4S cubed. Let me erase this here. Okay, so this is going to be 4S cubed because 2 squared is 4. This will be 4S squared times S, so that's 4S cubed. All right? So if Ksp is equal to this, the question is asking for you to solve for S. So that means that S will be equal to the cube root of Ksp divided by 4. And the Ksp value given is 1.17 times 10 to the minus 5 divided by 4. And then you find the square root of all that. And according to my calculations, this works out to be equal to 0.0143 M. And that's how you do that.
Would you find the square root or the cube root?
I'm sorry, cube root. Yeah, you're right, cube root. And that's the answer. All right. I don't know if I mentioned this before, but I have provided in Canvas a table which gives a list of the solubility products of a wide variety of substances. Let me just show you where that is located. Let me go here, and then, or you know what? Or let me go here and then files, and then tables. Where's the tables? right here. And the file labeled solubility product, that's the one. If you download it, it's going to look like this. So if you're not given the solubility product in the question itself, then you can consult this table right here, and it gives you quite a few substances. It's 6 pages long, so it's very comprehensive, all right? So of course, you'll have access to this table in your future tests, all right? Okay, so let me go back to...
I have a question about that.
Yeah.
When I went to take the test at the testing center, they gave me a packet that had some stuff in it, but they let me log into my student account on the computer that they have there. Was I supposed to go in there to your files to look at these charts?
No, they're supposed to provide a copy of it.
Okay, I didn't have any copies of anything like this. Is that because we weren't doing this yet, or?
Exactly, right. Yeah, you wouldn't have, right. So this particular table I showed you, you wouldn't have had it for your last test, but you will have it for your future test.
Okay, thank you.
Whenever I send over a test, I always send all the relevant tables that you're going to need for that test.
Okay, yeah, I thought it was a little weird that they were letting me sign into my Canvas. I'm like, I'm not doing any of this online, so I don't understand, but yeah.
Oh, okay. I probably need to talk to them about that. And by the way, since you said that, I've been having issues with the testing center because I've been trying to email them. Well, no, not email them. I've been trying to call them concerning the last test that you did. I have not received, well, I've received only 2 tests. I don't know, which I've kind of found weird because I thought, more people, of course, would be doing that test. So I've left a couple of messages on their voicemail. They haven't responded yet. So I'm going to try again.
Do you have the names to know if mine got sent over, or?
I can look it up right now. Let me see here.
Hey, Professor Pete.
Yes, sir.
I didn't get to take the last test because I was at a conference in Arizona, and I have to go to the testing center to take the test because I didn't get the email about the test, and I called them and they never answered the phone call, and I left a message of when I could come take the test.
Yeah, I've been having, oh shoot, I can't, okay. I just realized I can't access the email from here. So to answer the question asked by the young lady, I don't know who it was. I don't know if your test will be one of them because I can't access it right now. Because that's a regular college email, which I can only for now access from my desktop in my office. But to answer your question, the second person, who was it that asked the second question?
Garion.
Okay, so we'll have to talk about that. All I can say is that, like I said earlier, I've been having problems communicating with those guys over there in the testing center.
But they should still have the test, right? I should be able to.
They should say, right, they should still have it. It's just that I have to, contact them and let them know that I'm letting you doing it. But if I can't contact them, then how would they know to allow you to do it? You know what I'm saying? So
yes, sir.
That's what that's the issue I'm facing right now. But I'm gonna try to reach them later on after I finish talking to you guys. All right.
Okay, I'll just contact you after class.
Yeah, exactly. Yeah.
Okay.
Okay.
Professor Nicely, I had a question as well.
Yes, ma'am.
Is our next test next week, is it just on units 3 and 4, or is this unit going to be on it?
I have not decided yet. 3 and 4 would definitely be on it. Let me check something here. 3 and 4 would definitely be on it. I may include 5. I'll definitely let you know by tomorrow.
Okay, and is there any way you can unlock the practice test answers for unit 2?
I will definitely, I will definitely do that. In fact, now that I've mentioned it, let me see if I can do so now.
Okay, thank you.
So you're talking about past tests. Let Let me see here, test number 2. Let me just do a quick check of what test number 2 in the past says. Let me see here. Okay, let me publish that right now. Test number 2, summer 19. Okay, so it is now published. At least you'll have access to that, all right? But to answer your previous question, I've not decided yet. I'll let you know by tomorrow. I'm going to
We're on test 2, right?
Yeah. Well, actually, we're in the 5th chapter. Test 2, from what I saw here from past semesters, was based on what we did in the 3rd and 4th chapter. So
Okay.
the 3rd chapter was equilibrium. The 4th chapter was acids and bases.
All right. I'll contact you after.
Yeah. Okay. Any other questions before we move on? Any other questions? Let me do this. Okay, so this was question 4. Okay, very good. So if there are no questions and if there are no issues with question 4, let me clear this. And let me do this. And let me scroll down. Okay, so let's look at question number 5. Question number 5 says, I've discovered a new chemical compound with the formula A2B. If a saturated solution of A2B has a concentration of 4.35 times 10 to the minus 4, what is the solubility product? Constant for A2B. Okay, so this question is actually the opposite of what we did in the previous 2 questions. So basically, you're starting off with A2B, and it's going to form presumably 2A plus B2 minus. That would be the equation for the dissociation. Now, what the question is asking for is the KSP, right? And the question also gave you that the solubility is 4.35 times 10 to the minus 4, right? Now, initially, we would have none of that and none of that. So my question to you is this, based on what we did before, what do you think the changes will be for the concentration of A plus and B2 minus? And the hint is right here, the solubility. So what do you think the concentration, the change, I should say, in the concentration of A plus is?
Would you add 2 times the 4.35 times 10 to the
Exactly,
negative 4th?
2 times, right, 2 times the S, right? And what about the B2 minus?
You'd just be adding S.
Okay, very good. So therefore at equilibrium, you're going to have 2S and S here, right? And of course, KSP would be equal to what? What's the expression for KSP? Based on this here and this here.
Would it be the concentration of A squared times the concentration of B2 minus?
Exactly. So all we have to do now is plug in these terms into here and here. So you're going to end up with 2S squared times S, which would be equal to 4S cubed. And then all we have to do is put in, what am I doing? Hold on. All we have to do is, where we have S, we put this value here. So it becomes 4 times 4.35 times 10 to the minus 4 cubed. And when I did that, I got 3.29 times 10 to the minus 10. 3.29 times 10 to the minus 10. And that's how that is done. All right? Any questions about this? Any questions?
Why are we not square rooting?
Because we're doing the opposite of what we did before. In the previous question, or the previous question, we were trying to find S, and they gave us a KSP. In this question, we're given the S, and we're trying to find the KSP. So basically, this is the relationship between KSP and S, right here. KSP is equal to 4S cubed, right? If we were trying to find the S, then yes, you'd have to find the cube root of KSP over 4. But in this case, we are trying to find this. So basically, all we need to do is put the value of the solubility, which is given in the question, that's right here. We put that value where the S is, and then we do the calculation to get the final answer, which is the KSP. All right? Okay, any other questions about this before I move on? Any other questions? Okay, may I clear all this? Going once? Going twice? All right, let me clear this. Let me do this. And let me scroll down. Okay, so this question says, the solubility product constants are usually specified for 25 degrees Celsius. How does the KSP value of a chemical compound depend on temperature? All right, so this is something for you to, obviously no calculations will be required. So something for you to explain. So let me hear your responses. Let me hear what you think the answer to this question is. The question says, the question is basically asking, how does the KSP vary with temperature? So essentially what the question is asking is if the KSP value, will it increase with temperature or will it decrease with temperature?
Solubility increases with temperature, correct?
Right, the solubility increases with temperature. So how does that affect the solubility product?
Would it also increase?
Exactly, it will also increase because remember, the solubility product is basically the product of the concentrations of the ions, right? So if the solubility increases, that means that the concentration of the ions increases, and therefore that means that the KSP, which is a product of the concentration of the ions, will also increase, all right? So that's basically how that, that works out, all right? Okay, so that's the answer for number 6, the KSP will increase with temperature. Okay, now, based on what we did previously, you should be able to do number 7, right? So let me hear your suggestions as to how we tackle this particular problem. They gave you the molar, well, they're asking for the molar solubility of lead-2-chromate, and they gave you the KSP value for that. So what would be the very first thing you would write down? Oh, wait a minute, it's 10:49. All right, tell you what, we're going to stop here for the time being and then resume at 11 o'clock, all right? And then we'll jump on this question. All right, so I'll be back at 11. Okay, folks, I'm back. So this is where we left off. The question is asking for us to calculate the molar solubility of lead 2 chromate. And they gave us the KSP value for that same compound. So this is similar to something that we did before. So what would be your first step? Anybody? Well,
Would you try to write an equation for the dissociation?
okay, very good. So what is that equation? I need to keep track of who is talking. Let me see here. Who was that?
That was Rena.
Okay. So yeah, what would be the first? What would be the equation? I'm sorry.
Is CrO4, is that chromate?
Yeah, that is indeed a chromate ion. Yes, ma'am.
Okay, I'm not sure what the charge on that is, but would you split up into like PB? Yeah, and then it dissociates into PB2 plus
Plus.
CrO4, is it 2 minus?
Very good. So
Okay.
that's it. All right. So that's the equation for the dissociation. So the next step would be what? What would be the next step? Anybody?
Table.
Okay. So initially, what would be the state of affairs initially?
There would be, would you write a 0 on the product side?
For both lead 2 plus and chromate. Okay. And then the change would be what?
And then you would add plus S to each of
Mhm.
those.
Okay, very good. So therefore at equilibrium, you're going to have S and S here, right? Okay, what next?
Then would you write the equation for KSP?
Which is equal to what?
It's going to be the concentration of PB2 plus times the concentration of chromate.
Okay, and then what?
Substitute in S.
So that would be S times S, right? Squared, and then what?
So then you want to find S. So S would it be the square root of KSP, which is given?
So that's the square root of 1.8 times 10 to the minus 14. And that's whatever you get, that would be the answer. And when I did that, I got 1.3 times 10 to the minus 7. M. So that's the answer. All right. Okay. Any questions about that? So that's pretty straightforward for 7A. Now 7B is asking for the molar solubility of the same compound, but this time in the presence of this amount of sodium chromate. All right. So is it okay for me to clear this? Going once? Okay. So I'm going to clear that, and then I'm going to do this, and then I'm going to scroll down to this one. Okay, so in this case, they're asking for the molar solubility of the same compound, in the presence of this sodium chromate solution of this concentration, all right? So what I'm going to do here is write down the same equation for the dissociation, which is PbCrO4 dissociating to form Pb2 plus CrO4 2 minus. Now in this case, the initial concentrations will be a bit different. Now, can anybody tell me what the difference will be in this case? Let me give you a little hint. That's a hint right here.
Is it that you're going to have some dissolved CrO4 at the beginning?
Exactly. So basically this number will go here as the initial concentration of the chromate. The amount of lead 2 plus, the concentration will still be 0, all right? And then now the change would be, as before, plus S in each case, where S is the solubility, so that at equilibrium, you're going to have S here, but here, you're going to have 0.020 plus S, right? Now, as we did in the case of weak acid, we can assume that S is much smaller than 0.020. We can assume that, right? So that means that if we make that assumption, then 0.020 plus S will be approximately equal to 0.020, right? So therefore, we can write down the KSP expression, which is the same as before, Pb2 plus concentration times CrO4 2 minus concentration. But this time, you're going to have S here for the lead 2 plus multiplied by the 0.02, right? And that will be equal to the KSP. So that means that S would be equal to the KSP divided by 0.020. And the KSP is equal to 1.8 times 10 to the minus 14 divided by 0.020. And according to my calculation, that works out to be equal to 9.0 times 10 to the minus 13 M. So that's the solubility of the lead 2 chromate in the presence of 0.020 M sodium chromate. And there is a term that is used to describe this phenomenon. What is that term? Anybody can tell me? This is the concentration of the solution in the presence of a common ion, right? And what was the solubility that we calculated from the A part? 1.3 times 10 to the minus 7, right? So for the A part, for A, the solubility was equal to 1.3 times 10 to the minus 7 M. For B, the solubility was 9.0 times 10 to the minus 13 M, right? So obviously the presence of the common ion reduces the solubility of the lead 2 chromate from 1.3 times 10 to the minus 7 to 9.0 times 10 to the minus 13. So what's the name given to that effect?
Common ion effect.
The common ion effect, exactly. The common ion, which in this case is a chromate ion, basically suppresses the dissociation of the lead 2 chromate. So therefore, the solubility of the lead 2 chromate is lowered or decreases in the presence of a common ion. All right. Okay. Any questions about this particular question? Any questions?
I'm a little bit confused as to why we can assume that S is so much smaller than 0.02 in this case.
Well, because if you remember when you were introduced to the whole idea of solubility product, remember we said that this only applies to ionic compounds that are slightly soluble in water, right? So basically it is safe enough to make the assumption that the solubility of the particular compound, in this case lead 2 chromate, would be much less than the concentration of the common ion that is present. All right. So that's the reason why we make that assumption. And another thing, while we're at it, another thing I should mention too is that unlike in the case of weak acids and weak bases, we don't need to test that assumption, right? Because pretty much that assumption applies to every single sparingly soluble ionic compound. All right. So I hope that answers your question. Okay, any other questions about this before I erase this? Erase the writings? Okay, so I take it it's okay for me to clear all this, right? Okay, so let me clear that. And let me scroll down. Okay, now this one has to do with indicators. And especially those of you who are enrolled in my lab, you would, of course, have had the experience of indicators being used in the experiment that we conducted on Monday, when we were talking about equilibrium and Le Chatelier's principle and so on. Anyway, so this question says an indicator, HIND, is yellow in 0.1 M sodium hydroxide and blue in 0.1 M HCl. All right. So the first question is, write the equilibrium equation describing this indicator. So anybody have any ideas as to how to do this one? What would be the equation that you'd write down based on this formula here?
Would it be NaOH plus HCl? And then you write the double.
Oh, okay, let me stop you right there. What this question is asking, and maybe it's not clear enough, is the equation for the dissociation of this.
Oh, sorry.
So what's the equation for the dissociation of the indicator molecule shown there? Well, it should be easy, folks. Especially those of you who had me in lab yesterday. I mean, not yesterday, Monday.
Would it be H indicator and then the double arrows into H plus the indicator minus?
Exactly, IND minus. Okay, so that's the equation for the reaction. Now, based on the information provided here and here, you should be able to answer the questions, what is the color of this molecule? And what's the color of this? So what do you think the color of the HIND is?
Blue.
Exactly. Everybody understands the reason why it's blue? Who just answered the question? Hard for me to keep track here.
Andrew.
Okay, good. So, Mr. Watson, why do you choose blue as the answer? Is it a lucky guess or?
Because in the NaOH solution,
Mhm.
it's gonna like react. And so I know it's not that one.
Okay, so you're saying that in the case of the sodium hydroxide, the color is yellow, right?
Yeah.
Because so basically, what happens to this equilibrium in the sodium hydroxide? What do you think happens to this equilibrium? Will the equilibrium shift to the left or will it shift to the right?
The left.
You sure about that?
No, I guess not.
Okay, so the simple answer is the hydroxide ion will react with the H plus to form water, right? And the result of that is that the concentration of the H plus in this system will decrease. And according to Le Chatelier's principle, the system will try to shift in order to oppose that change. In other words, it's going to shift to the right. So therefore, in shifting to the right, if the solution is yellow, as the question says, that means that this would have a yellow color. Which means that if you put this in acid, it will shift in the other direction in order to reduce the concentration of the acid. And therefore, the solution becomes blue. So that's why the color, we can say that the color of the HIND is blue, and correspondingly, we can say the color of the IND minus is yellow. All right? Now, the question is asking here in the C part, what is the pH at the transition point of this indicator? Now, they gave you the range here, 3.6 to 5.2. So what would you say is the pH at the transition point? Anybody? Now remember, the range that is given is the range over which the color change occurs, right? So it's going to be acidic below 3.6, which means that the solution will be blue. And then from 3.6 to 5.2, there'll be a changeover from blue to yellow, all right? So by the time you get beyond 5.2, the color of the indicator will be yellow. So the question is asking, what is the pH at the transition point?
.2.
Why do you say that?
It's kind of just an educated guess, because if it changes, if it would change, like if it would turn yellow
Mhm.
after that point.
Yeah, well, that's true. It's going to turn yellow. It's going to be yellow from 5.2 and beyond. But the actual answer is that the transition point would be right smack in the middle of that range. You see what I'm saying?
Yes.
So what do you think the answer is, if that's the case?
4.4.
Exactly, 4.4. And of course, you get that because all you have to do to get that is add 3.6 to the 5.2 and divide that total by 2. And that will give you the actual point in the middle of that range. Okay, let me scroll down. Well, let me clear this first. And then scroll down. Okay, so now we're at D. D says, what is the value of the pKa for this indicator? Now, let me give you a little hint here. The pKa, let me see here. The if you have both A minus, I'm sorry, not A minus, I'm sorry, I and D minus and H, I and D minus in the mixture, we can treat it like a buffer, which means that the pH will be equal to pKa plus log of the conjugate base, concentration of the conjugate base, which is I and D minus, divided by the concentration of H, I, and D. All right. So that's one thing. And then the other thing that you have to remember is that at the transition point, the concentration of I and D minus will be equal to the concentration of H, I, and D. Right? Because that's halfway between where you go from the acid to the conjugate base or vice versa, right? So if these two concentrations are equal, then how do you determine the pKa?
pH equals pKa.
Exactly, the pH is going to be equal to pKa, right? So at the transition point, this here will be equal to 1. And at the transition point, the pH is going to be equal to pKa. So we know that the transition point pH is equal to 4.4. So the pKa is equal to 4.4, right? So that's how we get the pKa. It's going to be the same thing as the pH at the point where the concentration of both the conjugate base and the weak acid are going to be the same. So this brings us now to the question, then what is the Ka for this indicator? So how would you calculate the Ka if you know what the pKa is? What's the equation which shows the relationship between pKa and Ka? Let me write it here. Can anybody tell me? What's the relationship between the pKa value and the Ka value of an indicator? What is pKa equal to by definition? Well, somebody should know this. Hello, hello, anybody there?
I can take a guess.
Everybody's
is,
guessing today.
is pK equal to the negative log of Ka?
Exactly. Good guess. Okay, so, but what the question is asking for is the Ka, and you're given a pKa. So if pKa is equal to minus log Ka, then what is Ka equal to? And this is where your previous math experience will come into play.
Negative log of Ka over P.
Nope. No, 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 no.
10 to the power of pKa.
10 to the minus pK. Right? So not just 10 to the power pK, you have to put a minus sign here. And that's because of the minus sign there. All right? So that means that in this case here, the Ka value would be equal to 10 to the minus 4.4. And when I did that, the answer I got is 4 times 10 to the minus 5. And please note that I have 1 sig fig here because you have 1 decimal place here. All right? Okay, so any questions about that? Any questions about the E part? Okay, let's look at the F part. It says at pH 2.2, this indicator is the color, and it gives a space for that. And it's asking for whether or not the concentration of the weak acid is greater than, less than, or equal to the concentration of the conjugate base. Okay, so let's see now. pH 2.2, right? That pH is below the range, right? The range originally in the question is what? 3.6 to 5.2, all right? So what color would you expect the indicator to have at that pH?
Blue.
Blue. Why do you say that? Who said that? Miss McCoy? Why do you say that?
Because it's less than 3.6.
Exactly. And of course, anything below 3.6 for that indicator will give it a blue color. So the answer here will be blue, all right? So the next question is that indicator acid molecule, is its concentration greater, less than, or equal to the concentration of the conjugate base?
Less than.
Why do you say that?
I just figure it goes hand in hand since it's less than 3.6.
Well, let's go back to, in fact, let me not scroll up. Let me just see if I can squeeze it in here. Or tell you what, let me erase some stuff here. Let me erase all this over here. Because I think you need to actually see the equation in order to answer this question correctly. Okay, so now remember, the equation that you would have answered in the first part would be, do it here, HIND, HIND, dissociating to form H plus IND minus, right? And based on what we said earlier, the color of the HIND molecule is blue, and the color of the conjugate base is yellow for this indicator, right? So we already know that the color is blue, right? So again, I want you to look at this part of the question and answer which one of these would be true. Would the concentration of the molecule, the acid molecule, be greater than, equal to, or less than the conjugate base, the IND minus?
Greater than.
Exactly, would be greater than. All right. Okay, very good. pH 7.0. What would be the color of the indicator at pH 7.0?
Yellow.
Would be yellow. And what would be the answer for this part here? Would the concentration of HIND greater than, less than, or equal to IND minus? Anybody? If the solution is yellow in color, then which one would be of the greater concentration? Would it be,
IND minus.
I'm sorry?
IND minus.
Exactly. So therefore the answer here would be the less than sign here. The HIND would be of a lesser concentration compared to the IND minus. Okay, very good. Let me clear this and scroll down. Okay, so now we get to pH 11.3. What would be the answer? For the color, that is.
Yellow.
Yellow, okay. I'm sorry, let me do this again. So this is pH 11.3, yellow. All right. And which one would be of a greater concentration?
IND minus.
Okay, so the answer would be greater than sign here. And then now pH 4.4.
Wouldn't it be a less than sign?
No. Yes, you're right. Sorry. You're right. So this would be a less than sign here. Thank you. Okay, now in the case of 4.4, what would you expect the color to be? Now remember what 4.4 represents. It represents the pH at the right at the intermediate, right smack in the middle of the range where the color changes over, right?
Would
So
it be green?
exactly, it would be green because it would be an equal number of yellow and blue molecules, right? So therefore, what would be the sign that you would use here?
Equal.
Equal.
Equal. All right. And then what about pH 4.3?
Would it still be green?
Yes, I would say it's still be green, right? In fact, the general rule is when it comes to indicators, if the pH is within plus or minus, what's log of 10? Log of 10 is 1, right? So plus or minus 1, then the color would still be, you know, the mix of the two colors, right? So yes, green would be the answer again. And but in this case, the indicator molecule, which one would be greater?
The HIND.
Yes. So that would be the answer. Okay, very good. Now, in this case, in the case of K, they gave you 0.001 m nitric acid. So the question is, what would be the color of the indicator? Now, the key to answering this is finding out what pH is represented right here. So what do you think the pH of this solution is?
Without knowing that, I feel like it would be blue because you said a strong acid. So you're adding more acid, making it
Well,
stronger
true.
or lesser pH.
Yeah, that's true. But to be on the safe side, what I would do is calculate the pH, which is not anything difficult because it's a strong acid. The molarity of the H plus would be the same as the molarity of this. So the pH would be minus log of 0.001, which works out to be 3, right? And as you correctly said, you'd expect the solution to be blue because the 3 is less than the 3.6, right? And therefore, what would be the answer for this part here?
Greater than?
Exactly. All right. Okay. Then we get to L. Let me clear this here. Do that. Scroll down. Okay. Wait, which one? Oh, L. Okay. Oh, that's the last one. All right. So in the case of L, what would you say the answer is?
Yellow.
Yellow. And again, I would recommend that you calculate the pH in this case, which again is not too difficult because the pOH in this case would be equal to 3, which means that the pH would be equal to 14 minus 3, which is 11, which is above the higher range of, what was it, 5.2? So therefore, this would be yellow. And in this case here, this sign will turn around. So this would be the answer. All right. Okay. So that's basically it as far as this assignment is concerned. Make sure you complete this and turn it in. Today's what? Today's Wednesday. I would say turn it in by tomorrow. So let me, before I forget, open up a Dropbox for that assignment. So this assignment is assignment 5. Let me do that right now.
So, Professor, it will be due tonight by 12.
Tomorrow.
Okay.
Mhm. Just to give you some time to make sure it's properly done. Let me see here. Let me see here. Just to make sure it's opened up. Okay. And tomorrow's date would be the 20th. And let me just check one more thing. Okay, so now you should be able to upload assignment 5 into the appropriate Dropbox. All right. Okay, and again, let me remind you, make sure that it's submitted in a PDF format. Make sure also that you write your name at the top of every page, and make sure you do the assignment on the original document. All right. Okay, so in the time that we have left, and by the way, I don't know how many of you came in late, but just to let you know that I'll be ending class at midday, 12 o'clock today, because I have an appointment that I have to make it to. So we'll be cutting things a bit short today. All right.
So,
Yep.
Professor Pete,
Yes, sir.
can I contact you about the testing around like 4 o'clock on Skype?
Yes, I should be back. Yeah, I should be through with my appointment. Yeah, so call me on Skype by about 4 o'clock. Yeah.
Okay, thank you.
Mhm. Okay, so any other questions before I move on? Because what I want to do now is basically start off a discussion on the next chapter. Let me see if I can bring it up here, which will deal with thermodynamics. So let me get to the PowerPoint here. Okay, so let me publish this right now. So I'm just going to start off with this discussion, and then, of course, you're going to watch the videos on this very same topic, which will be available in Canvas under the modules link. All right. Okay, so basically, these are the topics that is covered under the general topic of thermodynamics. All right, entropy-free energy and how they relate to equilibrium, which we discussed earlier. All right. So first thing we're going to talk about is this whole idea of what we call a spontaneous process, right? And when it comes to that term, spontaneous, it means something different in chemistry and in the sciences compared to everyday language, right? Because the term spontaneous in everyday language sounds very dramatic, like talking about an explosion or something like that, right? But that doesn't mean the same thing in the sciences, physics and chemistry especially, right? So when we talk about a spontaneous process, we're basically talking about processes that will occur without any assistance whatsoever, right? It just happens, right? So what you see here is a list of examples of spontaneous processes. A waterfall runs downhill. A lump of sugar dissolves in a cup of coffee. Water freezes below 0 degrees at 1 atmosphere and melts above 0 degrees. Heat flows from a hotter object to a colder object. These are all examples of a spontaneous process. And here's another example. A gas expands in an evacuated bulb, and iron exposed to water and oxygen forming rust. These are all examples of spontaneous processes, right? So basically, as I said before, when we talk about spontaneous, a spontaneous process or spontaneity, we're talking about whether or not a process will take place unassisted, right? So as you can see in the picture to the bottom left of your screen, I'm sorry, bottom right of your screen, you see a skier going down the slope. That would be an example of a spontaneous process, right? Because the skier doesn't have to do anything. Basically, all he has to do or she has to do is stand on the skis, and gravity does the rest of the work, right? The non-spontaneous process would be the skier going uphill, right? Now, in order for the skier to achieve that, he or she would have to expend some energy in order to basically do a process which is non-spontaneous, all right? So that's the difference between the spontaneous process and non-spontaneous process. So to further discuss this topic, if you imagine this setup here, where you have two vessels connected by a stopcock right here, and you have a gas trapped in one of the two vessels over here on the left. When you open this up, we all know what's going to happen. The nature of gases are such that they will spread out and eventually fill out the entire volume of the two vessels connected to each other, right? So that expansion of the gas into both vessels or into the other vessel is basically a spontaneous process. Now, the non-spontaneous process would be the opposite, where all the gas in one half of the setup just moves into the other half, right? That would be a non-spontaneous process, which of course doesn't happen unless, as I said before, something is actively done, especially involving expending energy in order to drive that non-spontaneous process, all right? So the spontaneous process occurs unassisted, while the non-spontaneous process, some energy would have to be expended in order for that to happen, all right? So this brings us to the question as to whether or not there's a relationship between enthalpy and spontaneity of a reaction, all right? And basically what is found is that for most reactions, they are, well, let me put it this way. For most spontaneous reactions, they typically have associated with them an exothermic process. In other words, heat energy is usually evolved in a spontaneous reaction, all right? And one example is shown here, where methane reacts with oxygen to form carbon dioxide and water. That is a spontaneous process. It will happen, and it is also exothermic. Here's another example. If hydrogen ions combine with hydroxide ions to form water, that is also a spontaneous process, and that also has associated with it energy being lost in the form of heat, all right? However, there are a few reactions that are endothermic, but at the same time spontaneous, such as this process right here, the formation of liquid water from solid. That is a spontaneous process if the temperature is right. And that is also an endothermic process, right? I think I have another example here. If you dissolve ammonium nitrate in water, that is also a spontaneous process where the ions are formed, but you also see that delta H is positive. In other words, that process is endothermic. So based on the information that we see here, and not only this, but other examples as well, which I don't have here, what you find is that most spontaneous reactions either have a very large negative value for delta H or a very small positive value for delta H. In other words, spontaneous reactions typically are very exothermic, or if they're endothermic, they're not endothermic to a very great extent, all right? So this tells us that there's something else that you would have to use in order to make predictions as to whether or not a process is exothermic, or I should say a process, whether or not a process is spontaneous, all right? We cannot just simply look at the amount of heat released or the amount of heat absorbed to tell whether or not a process is spontaneous, all right? Okay, so there's another factor, therefore, that we have to look at, which basically will help us to make that kind of prediction. Enthalpy would be one of them, right? As we said before, one of the factors for driving any spontaneous process is that the reaction is either exothermic or endothermic, but not to a great extent. But there's another factor that we have to take into account, and that factor is something that should be new to you guys right now. It's called entropy, right? So what do we mean by entropy? Well, entropy is a measure of how disordered or random a system is, right? So basically, when we're talking about the entropy of a system, we're talking about how randomized the system is, all right? And we can, of course, tell just by, looking at how the system is organized or disorganized, whether or not the entropy is large or small, right? So basically, if the amount of order of the system increases, the entropy decreases and vice versa, right? So there's an inverse relationship between the order of a system and the entropy, right? Now, entropy can actually be measured, right? We can actually measure the entropy value of a system, or calculate it at least, and we can measure what is also called the change in entropy, right? So the change in entropy, which is, by the way, entropy is traditionally represented by the symbol S. So the change in entropy is delta S, and that is equal to the final value of entropy minus the initial value, right? If the change from the initial to final results in an increase in randomness, then that means that SF, S final, is greater than S initial, which means that delta S is positive, right? And then if the opposite is true, then delta S is negative, right? So just to give you an example, if you have a substance, and it doesn't matter what the substance is, and you compare the solid state to the liquid state, right? We all know how the solid state behaves and how the liquid state behaves, right? The liquid state would have the molecules moving more randomly than the solid state where the molecules are in fixed positions, right? So basically, just based on that idea alone, we can come to the conclusion that the liquid state is of a greater entropy than the solid state, all right? And therefore, we can extend that discussion to even the gaseous state as well. We can therefore conclude that the solid state would have a lower value of entropy compared to the liquid state, which in turn would have a lower value compared to the gaseous state, right? And that is true right across the board for any substance under all the conditions you can think of, all right? The gas would be more disordered and therefore has a larger entropy associated with it compared to the liquid, compared to the solid. And as you can see here, the extent of the entropy experienced by the gas molecules is much greater than that compared to the liquid, as indicated by this sign, all right? So if you're going to look at the transition going from solid to liquid water, from ice to water, right? Obviously, there will be an increase in entropy because the water would have a greater amount of entropy compared to the solid ice. So therefore, delta S for this change will be positive or greater than 0, all right? Okay, so just to give you some other examples, whoops, I'm sorry. So we just talked about this right here, going from solid to liquid. Delta S is equal to, or I should say greater than 0 for that particular change. The same is true going from liquid to vapor. Delta S is also greater than 0. And if you think about dissolving a solute in a solvent, right? That would also correspond to an increase in entropy, all right? So that is what is demonstrated here. And then finally, this might not be immediately obvious to you, but if you have a system at a temperature T1, and let's say you heat it to a temperature T2, so T2 is greater than T1, it doesn't matter if it's a solid, liquid, or gas, the entropy will increase, right? So for example, if you have a solid, let's say solid ice, all right? And let's say you have the ice at a temperature of, let's say, minus 15 degrees Celsius. And then you increase the temperature to minus 10 degrees Celsius. Then what happens as you go from minus 15 to minus 10 is that the molecules of the ice, even though it's in a solid state, the molecules will be in fixed positions, but they'll be vibrating around the fixed position. So therefore, at a higher temperature, the vibration will be greater. And therefore, as a result, the ice at 0 degree, I'm sorry, the ice at 10 degrees Celsius will have a greater entropy than the ice at 15 degrees Celsius. So that is basically what happens when you heat a substance. Its entropy will increase. All right, so if you understood what we just discussed, you should be able to answer the questions I'm about to get into. So this question is saying, how does the entropy of a system change for each of the following processes? All right, so the first one is condensing water vapor. Condensing water vapor. So what do you think is the answer to this one?
Entropy
Condensing wa-
will decrease.
I'm sorry?
The entropy will decrease.
Exactly. And that's because the randomness will decrease as you go from the water vapor to the liquid. All right. So you're correct. The entropy will decrease. Okay. The next question is forming sucrose crystals from a supersaturated solution. Forming sucrose crystals from a supersaturated solution. So what say you is the answer? Would that correspond to an entropy increase or decrease?
I would say decrease
You'd say decrease, why?
because I feel like the molecules are getting more compact.
Mhm. So yes, you're right. The randomness will decrease again. It becomes more ordered. So yes, the entropy will decrease. Okay, the next one, C, hydrogen being heated from 60 degrees Celsius to 80 degrees Celsius.
Entropy would increase.
Increase, exactly. Entropy will increase because now you're increasing the movement of the molecules. They'll move around faster. Randomness will increase and therefore delta S will be positive. Okay, the last one, subliming dry ice. Now, do you know what the term subliming means?
No.
Okay, so sublimation is when you have a solid going directly to the gaseous state without going through the liquid state. And if you're somewhat familiar with dry ice, you know that dry ice as well. Can anybody tell me what dry ice is?
Solid carbon dioxide.
Exactly, solid carbon dioxide. If you were to take a piece of dry ice and put it on, let's say, your bench top or your table, whatever, what will happen? It will simply evaporate and you'll see no liquid left on the surface, right? Okay, so with that said, subliming dry ice, would that be, what would the change in entropy would be for that particular process?
I feel like the entropy would increase rapidly.
Exactly, increase in entropy. All right, okay, very good. So now you get a feel for what this whole thing of entropy is all about, all right? Now, entropy is one of many state functions that you'll meet in thermodynamics. In fact, you have met state functions before, things like enthalpy, pressure, energy, temperature. Entropy is also an example of a state function. And just to remind you what a state function is, it is a property that is determined by the state of a system, regardless of how that condition was achieved, all right? And the analogy being used here, let's say that this represents a state function here, this represents a state function here at the top of the hill. It doesn't matter what journey you take going from the bottom to the top, the difference between those two state functions would be the same, all right? That's basically what they're talking about there. And here is a very small table of entropy values for different substances. And you can see some of the things that we talked about is quantitatively shown in the values indicated here. For example, H2O gas has a greater entropy than H2O liquid, as you can see comparing those two numbers. The same is true for bromine gas and liquid, that comparison, iodine gas and liquid, and so on and so forth, all right? Of course, I've provided, again in Canvas, a table which basically gives you the entropy values of different systems, all right? So again, that is something you'll have access to when you're doing your tests, all right? That table is much more comprehensive, of course, compared to the one that is shown here, all right? Okay, the first law of thermodynamics. You should have met this before, but bears repeating again in this course, which says that the energy of a system can be converted from one form to another, but energy itself cannot be created nor destroyed. Now, the second law of thermodynamics, I don't think you'd have met this before, but this says that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So what this is saying is that as far as the universe is concerned, the entire universe, the total entropy increases when you are dealing with a spontaneous process. So if you conduct a spontaneous process anywhere in the universe, then the result would be an increase in the entropy of the universe. If the system is an equilibrium system, then that will not change the entropy of the universe, right? So that's basically what the second law is saying. So just to summarize, for a spontaneous process,
Is that because in an equilibrium process, energy is just bouncing back and forth?
yes,
Not being changed.
yeah, pretty much there's no net change. How should I put this? I'm trying to find the best way to put it. I think the best way to put it is that there's no net change in the entropy itself of the system when it's at equilibrium. I think that's the best way to explain that. So to summarize the second law, for a spontaneous process, the total change of the universe, which is the system plus surroundings, would be greater than zero, right? Because it's always increasing for a spontaneous process. But for a process that is non-spontaneous, then the sum of the entropy of the system plus surroundings will be equal to zero. All right. Okay, one more thing, and then I'm going to call it today. We can actually, as I said before, measure the entropy of a system, and therefore we can calculate what is known as the entropy change of a reaction. Now, the values that you see in the table that I've posted are standard values, which means that these values were obtained when the conditions were 1 atmosphere and 25 degrees. And that is represented by the small o or 0 as the superscript there. So this is similar to standard enthalpy of a reaction that we dealt with in Chem 1. We can also have the standard entropy of reaction, and that's a change in entropy for reaction under these conditions. So if you have a hypothetical reaction, AA plus BB plus, well, not plus, to form CC plus DD, then to calculate the entropy change, we simply take the total sum of the entropy of the products, taking into account their coefficients, and then subtract from that the total entropy of the reactants, again, taking into account their respective coefficients, right? So to summarize, the change in entropy is equal to what you see here, all right? So just to give you a quick example, and this is going to be the last thing we're going to talk about. This question says, what is the standard entropy change for this reaction? So basically what you'd have to do is consult the table and look up the values, the respective entropy values for the different substances. And this is what you'll see when you check out the table. And then you plug the values into the equation represented here. Again, keeping in mind that whatever the coefficient is of the different substances, you multiply the coefficient by their respective entropies, right? So, so basically this is what you're going to get. 2 times the entropy of carbon dioxide minus the sum of 2 times the entropy of carbon dioxide plus that of oxygen. So when you plug the numbers in, you're going to get the final entropy, which is equal to minus 173.6 joules per Kelvin mole, all right? Okay, I'm going to stop here for today. You know something? Somebody asked me earlier if their paper was sent to me, their test paper. I looked it up. Let me see if I can find it here. Give me 1 minute. I was able to access my email earlier during one of the breaks. I know my computer is not turning on, so.
What is the test due for this week, Professor?
Okay, so that test will be given on Monday, and you have until the rest of the week. So that would be until Thursday to do it.
Okay, and then you said I can contact you between 4 and 5 about the last 2?
Yeah, exactly. Because I should be back home by that time.
Okay, I will.
Yeah. Let me just do a quick check of something here, because just to let you know whose papers have been sent to me. Give me one quick minute here. Let me see. Let me see. Give me a quick minute here. Come on, come on, come on. Okay, so the two persons whose tests I've received so far is McVeigh and Gennaro, right? So I have those two tests sent to me. I haven't received any others yet. Well, let me not speak too soon. Let me check. Let me check my inbox here. Oh, come on. What's going on here? Okay. This thing is so slow sometimes. Okay. Yeah, that's it. I received any other emails from them. So I don't know. Like I said, I'm going to call as soon as I finish with you guys here. I'm going to call them and see if I can get somebody.
Yeah, because I took my test last Thursday
Who
at
is
the
this?
testing center. McCoy.
Okay. All right. Oh, you took it on Thursday.
Yes, sir.
Okay. They sent me this Monday, this past Monday. So I don't understand why they didn't send yours. So I'm going to try and call them and find out what's going on. I
Okay.
hope I get through. I tried calling a couple of times and all I get is a voicemail. But I'm going to try this time and hopefully I'll be successful. So I'll
I
let you.
noticed when I called at 9 a.m. the other day, they actually answered. So maybe the earlier the better.
Well, actually, I called 8 o'clock this morning, right? And nobody answered. And I called later. I don't remember exactly when. I called later on. Nobody answered. So I don't know what's going on. Anyway,
What happens if you don't get the test from them? What if they lost it? Or
sure that I thought.
yeah.
I don't know.
Okay.
I don't know. I've never had that happen before, so I don't know what to say to that. But
Okay.
let me. I'll definitely. I'm going to push it.
Okay.
So as soon as I finish with you guys, I'm going to call over there. Okay. So that's it, folks. So I'm going to announce tomorrow exactly what topics will be covered on the next test, and also make sure that you send in the completed assignment number 5 tomorrow, so that I can have that graded and sent back to you. Oh, and by the way, I must apologize. I graded assignment 4, which I'm quite sure you saw the grades of. I was not able to, I scanned it, but for some reason, I was not able to send it to you guys via email because of something happening with Canvas. They said that I have too many something like sent emails in my inbox or what. I don't know what exactly it is. So I tried to delete, whatever. Oh, they said that I've sent too many attachments. I guess over the years. So
You mean
I was
assignment 3, right?
yes. What did I say? Assignment 4?
Yes, sir.
Oh, I'm sorry, assignment 3. Yes, I graded assignment 3, but I wasn't able to send it through because apparently I had too many emails and attachments. I didn't know that would be an issue. So I was trying to delete a lot of attachments that were somehow saved in this file folder, and that's taking forever. So I'm going to still work on that and try to get that sent to you as soon as possible, because you're going to need that also to review for your test. All right. So I'll try to get that as soon as possible done. All right. Okay. So if there are no questions or no other questions.
I have one more. I was gonna
Oh,
say,
yes, sir.
since syllabus is incorrect on the announcements page in Canvas, would you be able to tell us what the test schedule upcoming is
Okay.
past
So
this one next week?
Yeah, to answer that question, I would direct you to go to the syllabus, which is located in the files folder or the files link. So if you go to the files link and then go to the syllabus folder, you should see let me check and make sure here. You should see, hold on. Because I think I remember doing it. Let me see here. Syllabus. Right. So if you go to files and then there's a folder called syllabus, that's where the correct syllabus is. All right, the more updated one, the corrected one. So that will contain all the important dates, which include next week, the test for next week. All right. Okay, any other questions? Any other questions? Any other questions? Okay, so if there are no more questions, that's it for today. I'll see you guys on Monday. I'll be available, of course, for office hours on Friday from 12 to 5. All right, so feel free to contact me then concerning any questions or issues you may have. All right. Okay, so until then, see you guys. Take care. Enjoy your weekend.